All right, so this next problem should look somewhat familiar to you as we go through this. You guys did a lot of ladder problems back in pre-calc, if you remember. It's like every problem was a ladder problem. It was a little bit annoying, right? But as soon as you see this, a 17-foot ladder is leaning against a wall. What shape should you think of? More specifically, what kind of triangle? Nice. So let's sketch a right triangle here. Okay. And we're going to use, let's just use X, Y, and Z. So that means if I have a right triangle and I need to figure out missing pieces, what can I use? Yep, Pythagorean Theorem. So we've got x squared plus y squared is equal, and I'm just going to use, like I said, z squared for the hypotenuse. So we have a 17-foot ladder leaning against a wall, and if the bottom of the ladder, so that means right here, we're pulling, is pulled along the ground away from the wall at a constant rate of 4 feet per second, what is that? That means I'm pulling this way. What's the 4 feet per second? The thing you want to take. It's dx dt. It's the rate at which my x is changing. So they gave us dx dt is equal to 4 feet per second, right? How fast will the top of the ladder be moving down the wall? So what are we looking for? dy dt, that's my unknown. When it, meaning the ladder, is 8 feet above the ground. So what did they just give me? X or Y? Or Z? Yeah, they gave me my Y value. Okay. So, is my Y going to change? Yes. Each time the ladder is moving down, like here it's different, right? Is there anything there that won't change, sir? Yeah, my ladder. Okay, this is not an expandable ladder, okay? This is just a standard old school ladder. It is 17 feet long. So that is a constant value that will not change. And what that means is I can actually plug that in now. So remember what I highlighted in pink on the previous page? Okay, this is one of those situations where you can plug in first. So I've got x squared plus y squared is equal to 17 squared. So obviously, based on this unit, we're going to have to take the derivative of the whole thing. What's going to happen when I take the derivative of 17 squared? Yeah, it's a constant, so it becomes 0. So it goes away, right? So I'm not too worried about it. So when I do take the derivative, what's the derivative of x squared with respect to time? 2x dx dt. What about y squared? That's right. And then you told me the derivative of 17 squared is 0. So in my problem, obviously I'm going to need x, right? So how am I going to find x? I asked you about it before. Yeah, I'm going to have to use the Pythagorean Theorem. So we know what y is, and we know what z is. Z is 17. So we need x. So we have x squared plus 64 is equal to 17 squared is 289. Can someone tell me what x is? What's the square root of 225? 15. Okay, so here we have an x value, we have a y value, we had our z value, but it went away because it was a constant. We have dx dt, dy dt is what we want to find. Quick question, coefficients of 2's, can I get rid of those? Absolutely, you can divide everything by 2. Bless you. Again. Okay, so now we can plug in everything that we have and find what we need. So we have x is equal to 15 feet. dx dt, which they gave us, was 4 feet per second, plus my y value of 8 feet. We want dy dt, and this is equal to 0. Okay, go back to the last part of that sentence. It says, how fast will the top of the ladder be moving down the wall? What is this implying? What does it tell you about your answer, George?
It'll be a negative.
Absolutely. So that's okay, right? Because the negative indicates that the rate is bringing it down. Okay. So does it matter if I move this over here or this over here? No, it doesn't matter at all. So when I multiply 15, what is this, 60? So this is 60 square feet per second is equal to negative 8 feet dy dt. Okay, that means I need to divide by negative 8, right? Negative 8 feet. So dy dt is equal to 60 square feet per second times 1 over negative 8 feet. Okay, now remember, this is a, and I'm using air quotes, real life problem. So when you give this answer, it needs to sound like something we would normally say. So you might need a calculator. Can someone tell me what this rate is? You might be able to do it if you reduce and figure it out. Yes, sir?
Negative 7.5 feet per second.
Yeah. Okay, someone said in another class, negative 60 over 8 feet per second. Well, it's not false. I mean, that is true. But do you walk around saying, oh, yes, the ladder was falling at negative 60 over... I mean, nobody speaks like that. I mean, do they? I don't know anyone. So you said this is negative 7.5 feet per second. So another thing that you might say is the ladder is falling down at this rate. So if you did say that, you wouldn't give the negative, right? If you wrote it in the sentence form. Okay, so this is the answer. Okay, does anyone have any questions about the triangle problem? Okay. So this next problem is actually a good example because here we are talking about the sand pouring from a chute forms a conical pile. So as soon as I see in that first sentence the shape that I have, when I look at the formula for a cone, just compare the sphere and the cone. I know they're two different formulas, but what do you notice about the cone formula versus the sphere formula? Yes?
I mean, they both have, instead of having r cubed, because r would be like half the height of a sphere. I don't know how to explain this.
Think even simpler. Just look at it. You got more variables, right? I have an additional variable on the right. So if I am not paying attention to what I'm doing, I'm going to use the product rule and I'm going to make this problem so complicated. Okay, so this is where you have to be really careful. So a lot of times, this type of problem, especially for a cone, there will be a relationship given between the height and the radius, so that you can rewrite one in terms of the other. The common question that is posed, sounds so formal, is how do you know which one that you're going to replace? Am I going to replace the radius or the height? So you have to look and see what they gave you. So let's go through this problem and see what they gave us. So first of all, let's write down this formula. So the volume of a cone is, what is that? I can't see, there's a glare. 1/3 pi r squared h. Is that right? Pi r squared h. Okay, so that's the biggest thing. I've got two variables there, which if I can avoid it, I don't want it, because I don't want to use a product rule because it's going to become a hot mess. All right, so here it says sand is pouring from a chute that forms a conical pile, check, whose height is always equal to the diameter. Okay, that's important. They're not going to tell you something, well, they might give you some miscellaneous, but let's just write it down and see if it's important, even though I said it was. Height is equal to diameter. If the height increases at a constant rate of 3 feet per minute, stop. What did they just give us? dh dt. So we have dh dt is equal to 3 feet per minute. Okay, I'm going to ask you right now. You should be able to figure out which variable you want to keep right now. Do you want to keep r or do you want to keep h? They gave me something in relation to h. Right? And in addition to that, it says, at what rate is the sand pouring from the chute when the pile is 8 feet high? What is 8 feet? It's the height. So they gave me h is equal to 8 feet. So they gave me so much more about height than they did about radius, so now I should put in my head, all right, I got to get r in terms of h. In that last sentence, it says, at what rate is the sand pouring from the chute? What am I trying to find? Yeah. Think about it like this. You have this chute that is pouring sand out, and it's forming this cone sand-shaped pile. But remember, sand, it's not going to be hollow, right? Sand is filling up that space. So all of that space that is being taken up by the sand is the volume. It doesn't say it directly, but it's asking for the volume or the rate of change of the volume. Does that make sense? So you got to think about, like, in your head, visually think about what is going on and what does it create because it's sand. So they want to know dV dt. Okay. So here I'm looking at my volume formula. We have already discussed that we need to get rid of this r and write it in terms of h. And they said that our height is equal to the diameter. Okay. We talked about this before. What's the relationship of the diameter and the radius? Say it one more time.
R equals H over 2.
Okay. How did you get that?
Because height and diameter are the same. So, like, R would equal D over 2.
Mhm.
And H is the same.
Yes. So you made that jump where the radius is equal to half the diameter, and because these are equal, you said that r is equal to h over 2. And you're 100% correct, but not everyone can make that leap. No, that's totally fine. That's why I was like, I wasn't expecting that, so I was very impressed. Okay, so that means I need to take this and substitute what I highlighted in green over here. Okay? All right, so we're going to take this out and put this in. This is before we even take the derivative. So we have volume is equal to, can I write this as pi over 3? Is that okay with everybody? Pi over 3. Then I've got the quantity of h over 2 squared times h. So again, I know this is something you probably could do in your head, but I would recommend that you write it down. So V is equal to pi over 3 h squared over 4 times h. So I'm just taking it step by step. So that means that my new volume formula is pi over 12 h cubed. Does everyone see where I got that from? Okay, so now we need to take the derivative. So I'm going to start fresh right here. dV dt is equal to pi over 12 times 3h squared dh dt. That is my full derivative. Okay? I know I can reduce this, and I will in just a second. dV dt, that's my unknown, true? So it's in the right spot because this is equal to, this becomes pi over 4. What is h? Yeah, 8 feet. So I've got 8 feet squared times, what's dh dt? 3 feet per minute. Okay. This is 64 square feet. Does 4 go into 64? 16, right? Is that right? 16? So I'm going to write it down. So I've got pi over 4 times 64 square feet times 3 feet per minute. So 4 goes into 64 16 times 3 is 48. So that means dV dt is equal to 48 pi cubic feet per minute. That's your answer. Whenever you are looking at a rate for a volume, it's going to be cubed. Just a little hint. Okay? Questions on this cone question? Okay, this last one should not take us that long. Here we have an aircraft that is climbing at an angle of 30 degrees to the horizontal. So if we have a horizontal like this, and we have an aircraft that's climbing at an angle of 30 degrees, okay, we could create a right triangle, agree? Yep. Okay. If I want to know how fast the aircraft is gaining altitude, basically I want to know how fast it's gaining height. Okay, and we are given the speed. So the plane is speeding up like this, and here's the height. Think back to geometry. What's our relationship here? It is sine. You guys remember SOHCAHTOA, right? Opposite, hypotenuse. So we have the sine of 30 is equal to opposite over hypotenuse. What's the sine of 30? Come on. Yes, 1/2. And I want to get rid of this fraction. I don't want to use a quotient rule. So can I say 1/2 s is equal to h? All I did was get this over here. I didn't want to deal with a fraction. Can someone tell me what is 400 miles per hour? What's the label that goes with that? I heard it. ds dt. It says the speed, and it gives it per unit of time. So ds dt is equal to 400 miles per hour. So if we want to know the rate at which this aircraft is gaining altitude, we have to take the derivative. So this is 1/2 ds dt, which I know we have, is equal to dh dt. Put all the hard problems in the front. Okay? 1/2 times 400 miles per hour is equal to dh dt. What is dh dt? 200 miles per hour. Okay, questions? Yes?
Is the S and the ds dt speed or?
Yes. Anything else? Okay.